Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Now, over the last lecture, we are going through an exciting topic which is based on the ligand properties and not on the usually central in organometallic chemistry, that is the metal part. And from the ligand perspective, we are discussing sigma alkyl complexes or sigma donor ligands, and what we have seen that these ligands show a variety of binding modes to the metal center, displaying a rich diversity in binding, which eventually will translate into a rich unique chemistry that are attributes of organometallic compounds. In our previous lecture, we have seen how the sigma donor ligands, depending upon the hybridization of the carbon center bound to the metal, display such diverse binding modes. This binding can be classified into two types, mainly the terminal binding modes and the bridging binding modes, and a variety of organic moieties depending on their hybridized state bind to the metal center in bridging as well as terminal forms. As mentioned earlier, that sigma alkyl complexes are very important. Many of them are important intermediate in many catalytic processes, and hence it is important to have a full understanding of them. To get a proper understanding of the metal sigma alkyl complexes, it is important that one be able to prepare them. So, preparation of sigma alkyl complexes is a very important topic as far as these kind of organometallic complexes are concerned. And this lecture looks into the various methods that have been developed for preparing these sigma alkyl complexes. Another unique feature about these complexes is that depending upon the ligand's ability, pure metal carbon sigma bond can be supplemented by varying degrees of metal carbon by interaction. This is an important attribute of transition metal organometallic compounds, and this synergism is possible because of the partial occupancy of the inner d orbitals, and also is seen manifested in many sigma donor complexes. So, let us take a look at different methods that are used for preparing them. The first and the foremost is a method called metathesis reactions. that involves reaction between metal halides plus organolithium, organomagnesium, organoaluminium and organozinc reagents. So, these organozinc, organomagnesium, organotin are all sigma alkyl complexes. Let us see an example. For example, reaction with zirconium tetrachloride with 4 equivalents of benzyl magnesium chloride in ether gives zirconium tetrabenzyl. Now, what is interesting thing is that the product is a sigma alkyl complex and one of the reagent also is a sigma alkyl complex. So, the interesting bit is that if one were to synthesize this sigma alkyl complex by this method, then one needs a starting precursor which also is a sigma alkyl complex. So, one of the reagent has to be a sigma alkyl complex reacting with the metal halide to give another sigma alkyl complex. Let us take a look at another example. Platinum dichloride diphosphine reacting with these organolithium compounds gives the following chelated compound. Here too the product is a sigma alkyl complex, the way it had been discussed earlier in the earlier example, and one of the reagent too also is a sigma alkyl complex. Having said that, this is a very useful method, metathesis is a very useful method for and very common method for preparing transition metal organometallic sigma bonded complexes. Metathesis is also commonly referred to as transmetallation reaction. Transmetallation reaction and several examples of this include reaction of TiCl4 with aluminum alkyls Al2Me6 gives MeTiCl3. In this case, partial transmetallation of one of the chloride has taken place. NBCl5 reacting with dimethyl zinc giving Me2NbCl3, L2R PDX with Ar10 Me3 giving Me310X and L2R PD air. So, these reagents which are used in metathesis or transmetallation reactions are called transmetallating reagents. After this common method of preparing sigma alkyl complexes, another interesting method involves alkyl insertion or hydrometallation reaction. Hydrometallation reaction. And this involves reaction between a metal hydride and an alkene. As the name suggests, this reaction would involve insertion of alkene into a metal hydride bond. Let us see that with an example. For example, in this platinum hydride complex, but there is a platinum hydrogen bond, the reaction of that with an alkene, ethylene is showing over here, leads to insertion of alkene into the platinum hydride bond, giving a ethyl moiety. So, this is C2H4 plus 1 hydrogen from here, it gives you C2H5, a ethyl moiety. Here too, the product is a sigma alkyl complex, that is what we want to make, and the reactant, unlike in the metathesis reaction stage where the reagent was also a sigma alkyl complex, over here it is a sigma hydride complex. So, what we see that a sigma hydride complex is required to get to a sigma alkyl complex. And if we compare this reaction with our earlier metathesis reaction, what we can observe that in that case a sigma alkyl complex was required to produce another sigma alkyl complex. In this case, a sigma hydride complex is required to produce a sigma alkyl complex. We will illustrate this with another example in which iron hydride, dicarbonyl hydride bound to one cyclopentadienyl ring. So, this also is a sigma hydride complex reacting with butadiene, which is an alkene, a conjugated alkene, giving 1,4 inserted products. And also the geometric isomer. We will illustrate this with an example where a metal hydride complex, similar to the earlier example, a sigma hydride complex reacting with butadiene, a conjugated diene, to give a iron sigma alkyl complex with 1,4 insertion and producing both the cis and the trans geometric isomers. Here too, as one can see, the product is a sigma alkyl complex and one of the reagent is also a sigma hydride complex. A close variant of alkyl insertion is the carbene insertion reactions. Here the reaction involves again a metal hydride and a carbene. For example, the reaction of cyclopentadienyl molybdenum hydride tricarbonyl compound with diazomethane. Now, diazomethane is nothing but a carbene precursor, and similar to that of alkene insertion into metal hydride, here too we get the carbene inserted molybdenum compound leading to a molybdenum methyl CH3. So, the 3 hydrogens of CH3 comes from 2 hydrogens of CH2 and 1 hydrogen of molybdenum hydride, producing molybdenum methyl cyclopentadienyl tricarbonyl compound as shown below. This compound too is a sigma alkyl complex and also one of the starting reagent is a sigma hydride complex. Here too we see the same analogy what we had observed in the carbene insertion into metal hydride reaction. So far we had looked into metathesis followed by two variation of insertion reaction into metal hydride, one being alkene insertion, the other being carbene insertion, and now we are going to look at a very unique reaction for preparation of these organometallic sigma alkyl complexes. This particular reaction is extremely difficult to perform, as the intermediate species is highly reactive to air and moisture, and hence a very challenging method. This method is called metallate alkylation, and involves reaction between a carbonylate anion with an alkyl halide. An example of this is given here. We have a manganese pentacarbonyl dimer which has manganese in zero oxidation state, which is further reduced by sodium mercury amalgam to make a very electron rich metal species called metallate. Where the metal center is very electron rich, and then that is reacted with methyl iodide, where the carbon center is electron deficient, iodine is partially negative and this is partially positive. So, a rich metal center then attacks the methyl, eliminating sodium iodide to produce this methyl compound. Now, this is a sigma alkyl complex, but none of the reagents were a sigma alkyl complex or a sigma hydride complex like the other methods. So, in that way, from that perspective, this method is also very useful. This is successfully applied to another tungsten hexacarbonyl compound, which also has a tungsten in its 0 valence state, reacting with sodium Cp with elimination of 3 molecules of carbon monoxide, giving tungsten tricarbonyl metallate compound. In this case too, the metal center is highly electron rich, and when reacted with ethyl iodide, it produces the corresponding tungsten ethyl derivative. So, here too the final product is a sigma alkyl complex, but none of the reagents used were a sigma alkyl compound or a sigma hydride compound. So, from this perspective, metallate alkylation reaction is a very unique approach of making these metal sigma alkyl complexes. So, with this I would like to summarize the various preparative methods that we have discussed in today's lecture. In particular, we have looked at 4 preparative methods. The first one involved metathesis reaction between a metal sigma alkyl complexes with a metal halide giving another metal sigma alkyl complexes. This reaction is commonly called as transmetallation reaction. Next one was alkene insertion into metal hydride complexes, and following that the third type was also an carbene insertion in a metal hydride complexes. So, we had seen 2 varieties of insertion reactions for making metal sigma alkyl complexes. One was that of alkene insertion and the other of carbene insertion into metal hydride complexes, and the fourth one being a unique method called metallate alkylation, where low valent metal were reduced further to their metallate anions and which were then reacted with alkyl halides producing metal sigma alkyl complexes. So, with this we have looked into some of the preparative methods for making these very important metal sigma alkyl complexes. We are not done yet. There are few other very interesting methods that remains to be discussed, and their properties and their stabilities, which will be the topic of the subsequent lecture. I hope you are enjoying this exciting chemistry of organometallic compounds that are being discussed, and I hope that this would generate further interest in you in the topic. With this, I thank you for being with me in this lecture, and I look forward to being with you in the next lecture, which would discuss few more preparative details along with their properties and reactivities of these metal sigma alkyl complexes. Thank you.